Welcome. This is a reminder to myself about some work done from 2012 to 2022. It deals with Cauchy distributed random variables. First to the classical central limit theorem, which is taught in every probability course. It tells that the normalized sum of IID L2 random variables converges in distribution to the normal distribution. This theorem has a rich history. I made once a timeline of mathematicians involved in various versions of this theorem, from Abraham de Moivre to Boris Gnedenko. Let's get to high-risk situations. Montaigne and Stanley state in their book on econophysics that infinite variance is difficult to use, but that it is important, like in the risk estimation of financial systems. We see that illustrated here with a famous graph of the Dow Jones. Almost 100 years ago, changes can be rapid, faster than what you see in a usual random walk. Also, catastrophic events like wildfire or asteroid impacts can change the development of events drastically or catastrophically. Also, without catastrophes, if you look at stock markets, we see the Dow Jones of various firms during the last 10 years. There are sometimes fast changes. How can we deal with this? Here is an approach I followed especially in 2022. Define a class of random variables for which the mean exists in a Cauchy sense and for which the variance exists in a normalized way. The random variables do not have to be continuous. Here is the general definition, which also works for discrete random variables like the Basel distribution, which uses the zeta function at 2, or the discrete Cauchy distribution. These are examples of high-risk distributions. The high-risk central limit theorem tells that in this class the normalized sum converges to the Cauchy distribution. So here is the comparison. It's a nice high-risk brother to the usual central limit theorem. The distributions look similar, but the Cauchy distribution has infinite variance. The theorem follows from work of Levy, Kolmogorov, and especially of Gnedenko. Levy introduced the notion of stable distribution. The Fourier transform satisfies a functional equation, which, after taking logs, becomes solvable. We can take the case of alpha is equal to square root of 2, which is the usual central limit theorem, of alpha equal to 2, which gives the Cauchy distribution. Levy also looked at, of course, as the more general case, and there is a fixed point for this functional equation. Gnedenko then described the domain of attraction of stable laws. It can be found in the book of Gnedenko and Kolmogorov about limit distributions. I myself actually started to work with dependent Cauchy distributed random variables. If X has a uniform distribution, you can get Cauchy distributed random variables by using the cotangent function. And we can then look at almost periodic versions of this. Especially explosive is if you mix two potent mathematical objects together, the golden ratio, which is the simplest real number, and the cotangent function, which is the simplest periodic function. The reason why they are simple is that the continued fraction expansion cannot be simpler than for the golden mean. The cotangent function has the simplest Fourier transform among all periodic functions. Now put them together and build the Birkhoff sums. How does this grow? And we get a random walk which is completely solvable. So for L1 random variables, we have the usual, just the linear average growth. That's the Birkhoff-Ergodic theorem. But here the growth rate is not linear, so the sum doesn't grow linearly, but grows in a fractal way. That's the end.